So welcome. And what I wanted to give you first is a kind of survey of where you find the information. And some of you may not have taken courses at University of Oslo and may not be fully familiar with the standard setup. So there is an official website, which is the one I'm pointing at here. So if you actually just search for FYS5419, you will find this website. And here you will find the schedule, and you can actually subscribe to the schedule as long as you're registered with a UIO address. And then you can get a warning whether there are changes or not. So this is a kind of, I don't know if you looked into it, but there's actually the possibility to subscribe to these activities. There used to be a link here, but I see that they have taken it out, but it's probably somewhere. I didn't check that. And then what you will find down here is the weekly messages, which you will also get as an email. I have sent an email to all the people which were registered yesterday, but there are still people registering. So if you haven't received an email, just shoot me a mail today, and I will send you the email. But that essentially contains the information which you see here. We are also using Canvas, and we will use that one for handing in the projects. So Canvas is a place where you will also find the same message, which you will also get as an email. So I like to give a weekly update of where we are, what we are planning, and so on. So you will then find the weekly update here, and with a message of what we're planning to do. And everything is actually on GitHub. So I am assuming that everybody's familiar with that. If not, get familiar with it. We will not give any courses on that or any kind of introduction to it, because everybody has basically been exposed to that. So you can find all the material there, and you can just clone it and download it to your own laptops and use it as you want. So that contains lecture notes, projects, programs, etc. It's everything. And as you can see here from the official website, I've also put in a link to the weekly material, and there's also a link to the projects. I'm coming back to these practicalities. So there's a lot of information which is being duplicated or triplicated. I hope it doesn't confuse people too much. There's a list here of possible textbooks. You will find that in the weekly slides today. So today I will, to a very large extent, use slides. I will switch a little bit between whiteboards and slides, but it will essentially be a slides-based lecture, just to get people started. So I should also say a little bit about the course, the way it was set up originally. So originally, we did not have lectures. It was meant as a self-study course. But then, since there were quite many people attending, we decided to offer lectures. In the official schedule, there are no exercise sessions, but we have sneaked in a session, which is just a service to you guys, which we will have before the lecture. So I will give you weekly exercises which align with the projects, and then you can decide to come or not early in the morning and then discuss with us the exercises or anything else you want to discuss. Obviously, it cannot solve all your problems, but hopefully we can solve the problems which are related to quantum computing. And you will also here find a tentative weekly schedule, which you also find on the official website. And if you clone everything, if you're familiar with that, you can just clone everything, and then you can have a copy of it. And if you do a Git pull on a weekly basis, you will also get updates, because I keep updating all the information. Actually, the slides I sent you yesterday, they have been updated with some additional information. So that's about some of the practicalities here. I'm going to switch pretty soon to the slides, because they contain a little bit more information of what you find here. And also what you will see is that the video of the lectures will be added here, and the same with the whiteboard notes. So you can fetch everything from the weekly schedule here, or if you want to go into the doc folder, you can then find, if you go to the handwritten notes, you will find the whiteboard notes, which is actually my blackboard. In Pub here, you will find the weekly material. So typically you will find, if you like a PDF, you can look at that one. When we are going to run programs, the Jupyter Notebook will be the preferred, type of material which we will use. But I will often switch between a PDF and the whiteboard, just to slow down the pace, because just listening to slides continuously puts you guys all to sleep. And I hope you're not like me, whose attention span is something like 5 to 10 minutes before I start daydreaming. So hopefully I can break in and have some distractions here. And you can also find if you prefer an HTML file, which is okay for scrolling on mobile devices, feel free to use that. But in the lectures, I will essentially switch between the Jupyter Notebooks, whiteboard, and PDFs. Okay. So that was a little bit about where you find the information. I'm going to switch to the slides, because there are things I want to present to you and also discuss a little bit about the layout of the course. Okay. Any questions? I thought we could have a brief introduction in the break. I will also say a little bit more about, it's always good to get to know each other, what kind of expectations you have, etc., etc. But we'll do that in the break, if it's okay with you guys. I know most of you already. So let's switch to the slides and take a look at some basic messages which I wanted to give here. So let me find here our slides. So today, what I wanted to give you is a kind of motivation for why we do quantum computing first. There's a lot of blah, blah slides here, which give you a kind of survey of what we are going to do here. Then, unless you are forgotten everything, I would rather strongly like to emphasize that this course is actually very much based on linear algebra and elements of statistics. That is an essential part of quantum mechanics. So today I will also say a little bit about this, but a little bit also about the basic background and what you can expect from this course. There are many, many textbooks. And if you are familiar with the university library, typically the Springer textbooks are textbooks which you can download for free. So you would just log in at the university library with your UIO credentials, and then you can download the PDFs. So the university pays a fortune for subscribing to the different publishing houses like Springer, Cambridge, Elsevier, etc. So basically all the new textbooks which are being bought by the library are textbooks which you can download for free. And that applies to essentially all these. And since there's not a unique textbook I will follow, I will give you some kind of reading recommendations on a weekly basis where you can look into more mathematics and the mathematical details. So keep in mind that I would like to keep this kind of self-study approach to the course, in the sense that we are going to give you quite some freedom in doing what you want to do. So the chapters give you a kind of the chapters which I've linked here, they give a kind of intro to linear algebra and some of the basic mathematics. So if you wish to brush up your linear algebra knowledge, feel free to take a look at these chapters. I'm also writing on actually a bigger textbook on many-body physics, from standard methods to machine learning and quantum computing. And I will keep updating those notes, so you will also have access to those. So we will have weekly lectures with some exercise sessions and assignments. And these assignments are actually meant to align with what you need to plug into the project, so that gradually we build up the basic elements needed for the project. So we plan to have 2 projects, and they count 50% of the grade. I put a tentative deadline, so the deadline is for your planning, March 20 for the first one, and then June 1st for the last one. There is no final exam here, only project work. And this is to keep the spirit of the self-study part, because the second project is something which you can define. So the first project is something everybody has to do. Yeah? No, because I want everybody to be on the same line with the first project, because what we are going to deal with is something which is called parameterized quantum circuits. That's the basic keyword, which you will hear again and again. And in the first project, we're going to solve quantum mechanical problems. And that serves as an entry point, both to project 2, but project 2 is a project where you are, in a way, much freer to do what you want to do. But the first one is just written, set up as a standard kind of exercise-based project with a different score for every exercise. Whereas the second project is something which you should write as a scientific report. And you can see, so I like to call these advanced courses which I teach for the paper writing projects, in the sense that many of the topics I'm going to define for the second projects are projects which can become a scientific article. So you don't need to do that, but there are the possibilities. So some of the topics actually align with the present research topics. So the second project could be a continuation of the first, where you look at so VQE is the way you solve quantum mechanical problems to get the eigenvalues on quantum computers. And there are advanced methods, adaptive VQE. We are going to look at a simpler Hamiltonian, which then will allow us to make comparisons with analytical results and also exact diagonalization. Then in the second one, we are going to actually use libraries. So in the first project, you have to write all the operations from scratch. So no libraries, only NumPy or the standard libraries. No Qiskit, no PennyLane, no nothing. But in the second project, then since many of you would like to tackle more advanced topics, you will actually need to use libraries. If you're doing machine learning, then you have PennyLane, you have PyTorch quantum machine learning, etc., etc. And then I would typically recommend using them. So we have a whole series of topics here, and the applications and implementations of quantum machine learning algorithms is a hot topic. Studies of entanglement and physical realizations of quantum gates and circuits. Entanglement plays a central role in quantum mechanical problems. I should say that there is a model here which has been very much studied, which some of you have encountered in many-body physics, which is called the Lipkin model. And the Lipkin model has been used as a prototype for studying entanglement in many-body systems. And that's something which you can use as a starting model there. But we also have implementations of quantum simulators on real quantum computers. So we do actually have quantum computers you can access, where then you would typically write codes using Qiskit, which is a kind of a way to translate the operations into actual manipulations of quantum gates. I'm coming back to that. There are also the simulation of linear algebra systems, like solving differential equations, is a very hot topic, which is at the research front. Similarly, the implementation of quantum simulators is at the research front. We have something which is called the quantum approximate optimization algorithm. And this acronym is something which I always struggle with, QAOA. That's a famous algorithm. And if somebody's interested in implementing that one, take a look at it. So there's a lot of freedom for what can be done. However, what I will teach in the second half of the semester is actually about quantum machine learning methods, because that's in the title of the course. But you are not, you're free to do whatever you want to do in the second project. Okay? And there's another hot topic, which I'm very much interested in, and that's actually to implement quantum neural networks for physics-informed neural networks. That's also a very hot topic nowadays. And this brings you straight into present-day research. Last year, we had a group of people which implemented Shor's algorithm, which is one of these famous algorithms. And this is something I recommend if you have a good background in number theory. So number theory, classical number theory, is something which many physics and chemistry and computer science people have no idea of. It's often a topic which people who have bachelor degree in mathematics have seen. So unless you have that background, you won't appreciate Shor's algorithm fully. So I'm not going to teach about Shor's algorithm, but this is a possibility. And you can look at different projects of what people have done for the second project. Now, feel free to suggest other topics for the second project. Okay, so the second project is a project where you can use software and you can find, let me just show you, I have a list of softwares which is typically used. So you have PennyLane. PennyLane is excellent if you want to do machine learning. You have the Qiskit package, which is widely used by many people. Microsoft has a similar one. Qtip is, and QBraid, etc., etc. There are lots of libraries which you can use for implementing quantum computing algorithms. I have a list of textbooks. So we are trying to have these exercise sessions, but this is not something on the official schedule. That's simply because the department has not been willing to set up that, because that means obligations to assign a TA and use more money, but we're just doing it anyway. Then there's a list of textbooks here, and you can take a look at them. You can actually download all of them for free. Same with these two textbooks. So Maria Schult, she's actually one of the people who has developed the PennyLane software. And she has made an amazing career. You can actually look up her name, and it's quite impressive what she has done. And then we have the classic, Michael and Nielsen and Isaac Chuan, just called Mike and Ike. That's popularly called. And that's the one of the really reference textbooks. And then we have some other textbooks. The lecture notes by Preskill are excellent. So there's a lot of information here. And I will typically just link or point to some of these links for every week as a background material. So keep in mind that the lecture, as you can see from the slides as well, there's a lot of information. And we do expect you to actually invest some time on self-study. Yeah, this is, so I'm going to go a little bit quickly through some of these slides, but some of these slides here are going to set a little bit the scene for what we are going to do here. I won't say everything which is on the slides, but you can actually read yourself. But one of the things which we always struggle with, and for those of you who have taken a course in many-body physics, this is what you're confronted with on an everyday basis. So my background is in many-body physics, and I've been doing studied different many-body methods for something like 40 plus years. And the problem then is simply that you reach what is called the exponential wall, because you have a number of degrees of freedom simply explode. Some of the degrees of freedom do not show an exponential growth, but most of the degrees of freedom you have in quantum mechanical systems do actually have an exponential growth of states. So if you're thinking of a system, so this 2 to the n, which you see here, so if you have, let's say, 100 or 300 particles, and you're only looking at the spin degrees of freedom, spin up and spin down, so you have 2 possibilities. And that's why you see the number 2 here. That means that you can realize something like 2 to the power of 300 configurations. So configuration is a way to arrange the spins. So of the 300, you could have all 300 pointing up or all 300 pointing down. And then you have all the other possibilities. So this is simply something you cannot tackle on a normal computer. So the typical dimensionalities, if you use a method which is called full configuration interaction theory, which is an exact diagonalization in a basis, is typically on the order of 10 billion states or configurations. And 10 to the 82 is what we normally assume is a number of atoms in the from visible matter, observable universe. So without thinking of dark matter. Okay, so nature seems to be doing some extravagant amounts of computations behind the scenes. Now, if you now look at this exponential growth, so how do we actually tackle this? And this is what I wanted to say a little bit about as a kind of introduction to quantum computing. And I see that there is a comment. Yeah, just leave that one. So if you think of how do we actually, and I should also say quantum chemists who often do use the same type of methods. So we have something like 100+ years of experience. And this goes from simple implementations or approximations like the beta ansatz. You have perturbation theory, mean field approximations. You have standard computer simulations of many-body systems. And these are typical methods which are being used in the literature. And many of you have encountered these methods in different courses. So that would be the second answer. And answer 3, studying systems that allow for answers 1 and 2 above. Systems that are mostly classical or weakly interacting, so which normally falls within this box here, but also where you can express everything in terms of a single particle basis. So I'm throwing at you concepts from many-body physics, because what we are going to do actually is to solve a many-body problem. So we are simulating a many-body problem on a quantum computer. But we can also simulate algorithms on a quantum computer where actually the system we are simulating is a many-body system. So when you operate on a quantum computer, you're actually operating on a quantum many-body system. You're manipulating many-body states. Okay? So a quantum computer is actually you using quantum many-body physics to simulate something. So you let the physics or nature simulate the system for you. That's essentially what a quantum computer is. And many of these systems are actually relying on a single particle basis as an approximation. But you can actually simulate things with Monte Carlo methods. You can simulate strongly interacting systems, but that's often a little bit more difficult. But nowadays with machine learning and neural networks, you can actually simulate complicated, strongly interacting systems with quite some success. So you could say that the tools which we have developed over more than 100 years allow us to actually answer many of the questions which we are interested in. So, yeah, you've probably seen some of these statements. So simulating physics with computers, and this is actually what Feynman proposed, to actually use real physical systems to implement algorithms on real physical systems. And Feynman's motivation for quantum computers, the most obvious one, simulating quantum systems. And for physicists, this is actually kind of obvious things almost. Whereas for computer scientists, it sounded like a crackpot idea in the 80s. But then there's been a lot of developments, and one of the things which really ignited the field was Peter Shor's algorithm of factorization, which is very important for the encryption of data. And the standard encryption, which is based on number theory, is the one which people felt was really threatened if you could achieve a quantum computer. So this is just to give you a little bit of the background of the historical background which has led to the developments which we see nowadays. So if you look at Shor's algorithm, the typical statements which you will often encounter is whether quantum mechanics is wrong, there is a fast classical algorithm for factoring, for instance, or quantum computers are more powerful than classical computers. There's a lot of debate about these things. At least one of these should be true. And which one would you guys think is the most true one? What's the voice of the people? Number one, okay. Yeah, maybe. There's a lot of research going on. So I would also tend to say one. I'm biased, and I also would like to say three. If we look at the option one, what we would say is that it's actually one of the most successful theories of nature today. And in all its domains of applicability, we never found experimental disagreement. One of the really subtle experiments which have been done is the test of the Pauli principle. And within the experimental uncertainty, there is no sign that the Pauli principle is not valid. So many of these experiments are really, really difficult to perform. So what we can say is that within today's experimental uncertainties, there doesn't seem to be anything which breaks with the basic theorems of quantum mechanics. Now, what you could say, however, is that, okay, somebody could cook up a polynomial time classical factoring algorithm. And I don't know how much you've studied of Gauss, what Gauss has contributed. That's quite intimidating. So when I've been teaching computational physics and science for many years, and Gauss names comes up everywhere. So maybe there is a Gauss argument. If the prince of mathematics couldn't find it, then it probably doesn't exist. Okay. And quantum computers are more powerful than classical computers. And there are several arguments here. And you have something which is called the extended Church-Turing thesis, which a probabilistic Turing machine can efficiently simulate any effective computation process. So there's a lot of interesting background, which we will not cover here. So I'm just listing this as interesting background if you want to dive a little bit deeper and broaden your views on quantum computing and quantum information theories. Okay? Please interrupt me if you have questions here. Huh? So at least one of these statements should be true. I'm just going to leave that unanswered because this is part of ongoing research. So when you do research, you obviously can always test it experimentally. So some of the things cannot yet be tested experimentally. But as soon as you can test it experimentally and reproduce it, it becomes part of knowledge. And there's a lot of ongoing and very interesting research. So what I wanted to give you now is the essence of what you are going to do in this course. Okay? So a kind of naive statement, which you will often encounter, and is also a popular one, is that quantum computers can provide an exponential speed up over classical computers because the internal states live in an exponentially large space. If you have now 2 degrees of freedom, spin up and spin down, then it will be 2 to the n if you have an n-qubit quantum computer. Now, if you have more degrees of freedom than 2, suppose you also add spatial degrees of freedom, or you have other spin degrees of freedom. So suppose you have a spin-free half, then you can have 4 possibilities. And then it will be 4 to the power of n. So you would have even more arrangements. So this is something which simply takes into account a spin-up and spin-down system where every object is either spin-up, spin-down, or yes, no, true, false, etc., etc. So a binary system. And this is the most common one. And I will come back to this when we discuss physical realizations of bits. So the equivalent of a classical bit is the qubit. And despite this impossibility, there is something which I am going to emphasize quite a lot. And I want you to think of this statement in black here, or in bold actually. So what we are always looking after is to find a kind of deeper insight about the laws which govern the system. What does that mean? So I can mount a huge machinery. I have a big hammer. It can be a neural network, which I apply to a quantum mechanical system, which allows me to explore many, many more degrees of freedom than I can do with a classical algorithm. a standard algorithm like large-scale diagonalization. So if I use a neural network to find the best possible representation of, let's say, the ground state energy of the system, the neural network can have billions of parameters. If you think of larger language models nowadays, they have trillions of parameters which are being trained. That means you can get a perfect reproduction of, let's say, observables, but you don't get a deeper understanding of what happens. So what you often want to do in artificial intelligence and machine learning is something which people call explainable AI. So you want to use your machine learning solution to extract a physics or chemistry message. What are the basic degrees of freedom? So you have often very complex phenomena which have some simpler mathematical structures. So you have a huge space you can attack, but at the end, there are only some effective degrees of freedom which play a fundamental role. And when you do science, this is what you want at the very end. So a quantum computer is like a huge hammer, which allows you to smash on the system with huge dimensionalities, but then you ask yourself, what does this mean? This has actually consequences, quite some interesting consequences when you're doing quantum machine learning. And also any of the optimization algorithms, which we are going to discuss. Because at the end, we are going to do an optimization problem. So I'm coming back to this statement because this is actually quite important for what we will be doing in this course. So it's a very active field. So I'm going to skip some of these things here. Because so you can actually look at these. I mean, this is just a general blah, blah, but I wanted to say a little bit about hardware. So in Europe, we have LumiQ, which is a big European project. And this is a machine which we can have access to. And this coming week in Denmark, they are going to open up for QNorth, which is the Danish quantum computer, which is a 54 qubits machine, logical qubits. And it's going to be operative towards the end of the year. And that's going to be one of the most advanced machines which we have access to. So there's a lot of things happening here. I wanted to say a little bit, I'm going to skip some of this because I wanted to say, I'm coming back to this, but I wanted to say a little bit about what this course is going to be like. So a quantum computer is a well-controlled, out-of-equilibrium quantum many-body system that one intends to use to perform a calculation. So I'm manipulating physical states in a system by lasers or other external probes. And this is something which then is being translated into what we are going to call gates. And this is a kind of abstract representation which is used to describe the quantum algorithms. So this is normally called the gate-based quantum computer. But what does it mean mathematically? Let's just look at that so you have an overarching view of the things you're going to struggle with throughout the semester. So one thing, and this is actually a very delicate thing in quantum computing, is to prepare the initial system. So the abstract gates is defined as follows. So you have a set of n two-level systems, which are normally called quantum bits or qubits. So typically, and I'm going to switch to the whiteboard just to give you a kind of feeling of what that is. So let me just put up the whiteboard. So you can think of a system, and in solid state physics, this is one of the typical realizations, and one of the platforms is called quantum dots, which you now can idealize to something like a set of wells which are being set up by electric fields, for instance. You can set up electric quadrupole fields which look like a harmonic oscillator. This is a technology which was used for Bose-Einstein condensation and a chain of Nobel Prizes in the 90s and into 2000. So you can then set up electric quadrupole fields. And if you have a harmonic oscillator, you know that these states here, so you can call this system A, and then you can make a new one. So this can actually be designed in an industrial way. So this is the quantum engineering part. Now, system B, so in principle, these harmonic oscillator lookalikes have many states. They are not like a harmonic oscillator, which has an infinite set of bound states. At a certain point, the particles can escape. You can then trap either single electrons. This can be realized experimentally, and people have done that. So you could think of this being a single electron in system A, then you have system B, you have system C. And then the lowest lying state defines what we will call bit 0. And we'll put an A on that one. And then the first excited state could be bit 1. So we normally represent that in terms of a two-dimensional system, in the sense that we have two states, but then you have an infinity of other states. Now, the hope is, in this kind of systems, the hope is that you can isolate these systems pretty well experimentally and be able to manipulate them. And that can be manipulated with magnetic fields, which would interact with the spins. So the spin qubits is something which is a very actual way of a very important experimental way of realizing entanglement, which we will come back to. If you look at the next system, you could then identify a low-lying state here and a low-lying state here. And then in principle, what you would be doing then is to neglect what comes up here. So it means that you would simply neglect these other states. Or you could include higher states. And that leads to something which is called qubits instead of qubits. So you can actually do manipulations with more states. We will essentially here stay with a qubit realization because that's what most platforms nowadays do implement. So you could now think of a chain of these types of traps where you now have isolated, let's say, a single electron. And in this state here, so in principle, this state, you could prepare this state here would be the tensor product. And I'm coming back to this a little bit later after the break. So 0 of system C. And we would typically label that one as something like 0, 0, 0. Yeah.
Is there any advantage to using qubits instead of qubits? Why do you want?
So technologically, the thing is that in many of the states which you have in the realizations, you will often quickly hit the continuum of states. And then it's difficult to manipulate these higher lying states. So it's very much whether you use just two states, the two lowest lying states, depends on the system you have. Because you can quickly reach here into a continuum of states. And then it's very difficult to manipulate these states experimentally. So what you want are well-distinct states with a certain lifetime. Yeah.
You did manage to create qubits.
Yeah.
Would they be better computation?
Yes, it would actually. But the whole thing is that when you devise many of the algorithms nowadays have simply been based on qubits. And there's a lot of research actually on qubits and qubits, et cetera, et cetera. So this is an open research field. Many of the reasons for why this hasn't taken off fully, it's simply due to the experimental realization. Okay. So physically, what we are doing is that we are using this system and we are going to manipulate that system. And one of the, so everything we do now in quantum computing contains 3 stages. One, so let's just write them down here. One, which is the initialization. And that's difficult by itself, experimentally. So as a theorist, you could simply say we prepare the system so that let's say these electrons are all in the lower states in their respective harmonic well lookalikes. Experimentally, it can actually be quite difficult to initialize the system. So that's a part by itself. But suppose you have initialized the system. And this is one of the things we will always do. And we will typically write this out in terms of a given state, which is our initial state. Then what we have is the time evolution of the system. And this is how we implement different algorithms. So the time evolution could be your system now being perturbed by a magnetic field. And one of the things you want to achieve experimentally is that you can consider these systems as isolated systems and independent of each other and not identical. That's a very important aspect, because then it means that you can say with quite some confidence within Heisenberg's uncertainty relation that when I act with suppose an electric field on the system, it acts on only one of them. So I can do what's called one-qubit operations. So the implementation of an algorithm is actually based on you setting up operations of different external probes as a time sequence. So that means that there is a time evolution operator which acts on the initial state. And then the final stage, which is also a tricky one, is a measurement stage. So these three stages which you see here, they define the exciting research field of quantum control. So there can be quantum control parts which only focus on the measurement side, which is actually pretty difficult to extract from measurements whether you were in a specific state or not. Because when you do a measurement, then you know that the wave function collapses to just one of the possible realizations. So if you have a zillion of intermediate states which exist during the time evolution, when you make a measurement, the system collapses to a classical system. So if you look at these states here, even though we do quantum mechanics, I would typically call these for classical quantum mechanical states. And they make up what I will later call my computational basis. So theoretically, it's very easy for us to define a computational basis. Experimentally, we need to identify systems where we have states which have a long lifetime, which we can manipulate, which are well separated in energy, and can, within the frequencies of, let's say, a laser pulse or whatever, they can actually be operated on. So experimentally, there are many, many different platforms which try to realize qubits. So we will abstract ourselves a little bit from the experimental side, and we will simply assume that this is something, the initialization is something which can be done. And then we are going to set up algorithms where we act on the state. So essentially what we are going to do now, if you look at part 2, suppose we have an initial state psi, and I call this initial, at a time t0. Then the psi final is something which is given by a time evolution operator. So this is at the final at a time t, and you start at a time t prime. And this acts on the initial state, initial, where you have time prime, and here we have time. So these operators are unitary operators, and they define the time evolution of the system. This time evolution of the system is actually you applying different external probes, like a laser or magnetic field, on the system at given time steps. Now, the operation of these different probes they are translated into what we call quantum circuits. So that means that the operation of this guy here, this one, is something, suppose now we have an initial state which is given by qubit 0 in system B and qubit 0 in system A. This is the initial state. And then we operate with, let's say, an electromagnetic field on the first qubit. So that could be us going back here and having a laser which now excites this one to the first state. So the laser frequency are tuned to do that. Then this will be the gate here, which I'm just writing with an X here to just stand for 1 qubit gate. So this is a mathematical operation, but it's reflected in a physical process. So we are taking physical processes which we translate into mathematical operations. And then we write these mathematical operations in terms of what we call a circuit. So that's the basic language which we will be using. And then you can have gates. So you can have a 1 qubit gate. You can do the same on the second one, or you can have a gate which where you entangle states. And then you end up with a final state here, C final. Now you have not done a measurement yet. So depending on what you have done, this final state can be entangled or it cannot be entangled. We are coming back to what that means. So this means that, and actually this is a kind of hobby horse I have when it comes to teaching quantum mechanics. So if you're not too familiar with quantum mechanics, this is a very nice way to understand what quantum mechanics is. Because quantum mechanics is an operation on physical states with external probes. You initialize the system in a specific way. You perform some operations. And these operations which you see here, they are going to reflect different algorithms. So from a theoretical point of view, this looks like a very abstract thing, but it is actually us implementing this physically on a physical system. So it's the physical system on a quantum computer which does the operation. Now, project one is actually going to be us writing the different gates, but we will simulate them on a classical computer. And that's why we will write everything from scratch ourselves in order to get familiar with what these operations mean and how we perform the measurement. So when you have performed this final state here, we haven't done a measurement yet. Depending on where you make the measurements, and there are many clever techniques in quantum computing nowadays, where you can exploit quantum mechanical interference, where you can make measurements inside the circuits and then peel off some states you don't want to have, and then continue till the desired goal. So there's a lot of interesting manipulations which you can do on actual quantum computers. But this one, which you see here, in a way, reads like music. So if you read your music, you could think also one line where you have the different notes, the second line, etc., etc. So it's a very nice way of understanding what happens physically with a quantum mechanical system. So I would say that quantum computing, if you teach that one, when you teach quantum mechanics, is perhaps a path to a better understanding of what is actually taking place. That's a personal bias, okay? After having taught these topics for 40 years. Okay, so we should take a small break. I went a little bit over time. And then after the break, because essentially what you will do in this course is the steps: 1, initialize the system; 2, implement an algorithm with different gates; and the final step, measurement. And that's it. That's basically what we will be doing again and again. And when we do many of these algorithms, there will be parameters where we then entangle the states. And these states are going to represent a quantum mechanical best possible representation of a physical system or a given thing we want to do. And then we need to optimize the parameters. And that's where the optimization part kicks in. So I wanted to take a little bit more time just to give you the overarching view about what we are going to do here. And then after the break, we are going to do some very exciting linear algebra, which everybody's looking forward to. Okay, let's take a small break. Okay, as we said before the break, the way we are going to, how to say, the different steps we are going to look at in this course, they are given by this kind of trinity of initialization, the time evolution, and the measurement. That's essentially what we will be doing again and again here. And we are going to translate the different physical processes, like you interacting with one of these particles. These could typically be electrons. And people have actually realized systems where you can trap a single electron, or you can have complicated many-body systems. Some of these are called quantum dots, which are actually electrons confined in small regions between layers and semiconductors. And you can actually fabricate this on an industrial level. And people are using quantum dots, which are more complicated many-body systems, or you can isolate single electrons. You can have ion traps. These are different types of platforms, which are being widely explored scientifically, both from a quantum engineering point of view, but also from a theoretical and experimental point of view. So the thing is that this is a field which promises a lot, and at the same time contains a lot of interesting science which can be done. And finally, we will express many of the basic algorithms in terms of these graphs, which are called quantum circuits. And as I said, to me, that is almost like reading music. And hopefully that can also increase the intuitive understanding of quantum mechanics. So let's switch back to the slides. So I'm going to use the slides a little bit throughout this lecture. So what I wrote on the whiteboard is that we are going to have some kind of abstract-based quantum system. And the kind of preferred approach is that we have a two-level system. That's the standard one, because often many of these systems have very few distinct discrete levels, which are well separated in energy, and where the energy difference is something which aligns with the frequency of a laser or of a magnetic field or whatever, which is being implemented. And then you will have a continuum of states, which are more difficult to handle experimentally. So the kind of preferred mode in many of these textbooks, which you will see, experimental implementations, etc., is that of two states, which we label as 0 and 1. And the most general state is then just a combination of all if you have n such two-level systems. So I'm coming back to the mathematics here. Right? And the sum runs over all the qubit values, which can be 0 and 1. And this one here is actually a short for a tensor product. So I'm going to break this down a little bit later, so you see more the mathematical details. Okay? So now just look at this as a complex state. And the thing is that when you deal with a quantum computer, you can, as an intermediate state, before you make a measurement, you can then actually have a state which contains all possible realizations of your Hilbert space. But when you perform a measurement, then the system collapses to a specific state. So essentially, you would initialize it, as we said, and then we have a set of unitary transformations. So unitarity plays an important role. I should also say that the systems we will be looking at are essentially isolated systems. Isolated systems in the sense that the particles don't escape from the system. So if I have 10 electrons in 10 traps, then the system is going to stay like that. Unfortunately, experimentally, these particles can escape due to external perturbations, etc., etc. So one of the problems with many of the quantum computers which are being realized is that you're cooling down the system to essentially 0 Kelvin. That applies to superconducting qubits, quantum dot qubits, ion traps, etc., etc. They are not done at room temperature. This is also in order to realize quantum mechanical effects, but that means that we need a lot of helium-3 to cool down the systems with dilution fridges. And you probably know that there's a shortage on the Earth on helium-3. There's actually a Finnish company from the University of Aalto, which is world leading on making these dilution fridges. They have a price tag of roughly $1 million each. So in order to conduct experiments with quantum computing and to run quantum computers, you need to cool them down. And like one of the problems we have faced is that if many people are using the quantum computer, then you can easily destroy what we, before the break, call the computational basis, because you have thermal excitations. So the system gets heated up. And if it gets heated up, then your computational basis breaks down. And you just get garbage out. And then the system has to be reset, which essentially means cool down, and you have to set up an initial state. So the initialization is a very important aspect of what we are going to do, we are not going to initialize the system. We are just going to assume that it has been initialized. And then we have the standard time evolution, where T is the time ordering operator. Some of you are familiar with that. We will come back to these things. And then in physics, the system is described by a Hamiltonian, which is time dependent. And that could be some interactions between the particles, plus some external field, which is time dependent. So you can have a laser pulse, which you switch on and off. And the different evolution operators that one will use, they're called gates. So that's the kind of language we will be using. So what we are doing is, if you think of that figure about the quantum circuit, is that we are expressing algorithms in terms of quantum circuits and these gates. And these gates is just a pictorial way of illustrating the physical process acting on the system. And a single qubit is one which actually operates on one qubit, just one of them. So that means that there is an operation on one of them, where typically, and this is something we will come back to pretty soon now, is a unitary matrix. And in terms of the wave function, such a single qubit gate translates into a matrix which acts like this. And we are going to break this down example by example. So we will start with a 1 qubit case, and then we're going to a 2 qubit case, and then we're going to increase that to more qubits, just to increase the complexity. And if you have a 2 qubit gate, that is normally a 4x4 matrix, and I will come back to why it is that, so that you see the math. So this is just taken at an overarching view at it, and these are typical gates. So we are going to encounter the Pauli matrices. Actually, one of the things which we, and which you will see again and again in most of the applications, is that people often have used Hamiltonians which only have the spin degrees of freedom. And some of you may have encountered models like the Heisenberg model, the Ising model. These are all models which can be rewritten in terms of Pauli matrices. And these Pauli matrices are important makeup, important mathematical representation of physical processes. So a 1 qubit gate, it can often be written out in terms of these different Pauli matrices. Then there is another important gate, which is called the Hadamard gate, which sets up a superposition of states. And we're coming back to that. And then we have phase gates and different rotational gates, which we are going to discuss in more detail. And then there is a gate which acts on 2 qubits, which are different types of control gates. So you can see that this one acts on the first one, and this acts on the second one. You will see that in more detail when we go through the mathematics. So this is something which I still want to keep at a kind of overarching level. So the whiteboard notes, which I gave you before the break, they actually contain an example of a 2 qubit gate. And this gate actually entangles a state. It creates a state which cannot be decomposed into products of single particle states. So we are coming back to entanglement. Entanglement plays a central role in anything which we do. Then the last ingredient is the measurement, where you simply look at for one of the realizations, where the alpha is 0, 1, and then you simply perform a measurement, and then the new state is actually going to be given by this normalization factor, and then it's going to have a new state of the system. So nowadays, many of these quantum compilers, they do also measurements at an intermediate step in order to exploit, in some of the algorithms, you need to exploit quantum interference. So some people may say that quantum interference is just an aspect of superposition, but quantum interference is actually something which plays an important role in many quantum algorithms. So making measurements before the final state is something which can be used to tune the states. We are coming back to all these topics. So in a nutshell, a quantum computer allows one to perform a subset of linear algebra, essentially matrix vector multiplications. But then some of the algorithms which we have are more heavy linear algebra tools, but everything we are going to do is to break down into linear algebra operations, which at the end look like matrix vector multiplications. So the appeal is actually due to the fact that you can realize intermediate states which access the whole Hilbert space. But obviously, when you make the measurement, it collapses to a specific state. As I said here, the downside is that one does not hold the corresponding exponentially large vector of 2n values, but only a much smaller set, and n bits of information actually. And then you get a simple sample of the distribution. And that's normally what's one of the Achilles heels of quantum computing. The other one is something which is called decoherence, which we will happily put under the carpet throughout the course here. And that's the really big issue, actually. How long does a state you manipulate live? So we will assume when we implement the different algorithms, so the focus in this course is on the algorithms and the implementation of the algorithms. So we will, as I said, we will leave these as a topic for quantum engineering. Okay, so I'm going to skip. I just wanted to go back a little bit to some basic motivation here. So when we look at quantum computing, there are some basic concepts which you will now encounter again and again. And one is obviously superpositions. So these qubits can exist in a combination of states. Superposition, it's not only something you have quantum mechanically, but you know that classically you have classical superposition. That's pretty standard. Think of a Fourier transformation. That is just a superposition of different states, of your computational states, which in principle you can think of, even if they are quantum mechanical states, they can be thought of as classical computational basis states. Then entanglement is a type of correlations which you don't have classically, which is exploited in essentially all the algorithms. So when you are going to solve Schrödinger's equation for a many-body system, we are going to entangle the qubits. And the way we entangle it and perform these operations and the parameters which are related to that form part of the optimization problem, which we are going to study. And you will see that if you don't entangle, you will not get a proper description of the ground state of the system. So entanglement is an important aspect, which we will come back to again and again. And then for some of the quantum algorithms, quantum interference is actually very important. And we will look at that in some of the algorithms as well. So these are the three key components in many of the algorithms. And then clearly quantum parallelism, you can actually process multiple states simultaneously. Then you have quantum entanglement and also quantum interference. And one of the classic algorithms which shows a great speed up was Grover's algorithm, but also Shor's algorithm. These were algorithms developed in the 90s, which really spurred a huge interest in quantum computing. The limitations obviously are, so we live in something which is called the noisy intermediate scale quantum devices. The coherence time plays a very important aspect, and limited qubit coherence times. These states which we're looking at often have a short lifetime, which makes it impossible to manipulate them with different external probes. Also, when you do quantum machine learning, there is another topic which is non-trivial and where there's a lot of research, and that is about efficient embedding of classical data. And it's also difficult to scale circuits to large data sets. So these are problems which we face, in particular if we do quantum machine learning. And then you know that there are some of the basic fields of application. So we are not going to deal with quantum communication, like quantum teleportation, etc. So I'm just listing that as one of the big. So when we talk about quantum technologies, we're actually thinking of quantum communication, quantum computing, and quantum metrology. These are the three big issues. And when somebody says quantum technology or quantum information science, we often think of this as three main research directions. So this is a topic which we will not discuss, neither will we do quantum cryptography. We do actually have research at the university here at the Department for Computer Science. So this is a very active research field. But then quantum computing is the one which we will deal with. And obviously also there are ramifications to quantum metrology when we deal with this. You can actually show that if you have entangled states, you can increase the precision of an experiment. So these are topics, if you're interested in that for the second project, we can define something along those lines. And then if you look at the challenges which we have for quantum entanglement, you will see that entangled states are often fragile. They have a short lifetime. Decoherence time is a big issue. Interaction with the environment collapses the wave function. You can have something like thermal excitations because the system is being exposed to thermal excitations, just to give you an example. There's a lot of research on how to entangle large number of qubits. And this is actually something which has to deal with fundamental aspects of quantum mechanics. So you can actually, experimentally nowadays, there are experimental programs to study many-body entanglement. So that's a fundamental aspect of physics, which you can study with many of the experimental realization nowadays. Yeah, you can also read many of the statements which we have here. And then quantum machine learning, that normally integrates, which we will discuss in the second half of the semester, integrates quantum computing with machine learning algorithms to exploit quantum advantages. And high-dimensional Hilbert spaces, quantum parallelism, faster computation, and quantum entanglement for richer data encoding. These are some of the key advantages of quantum machine learning. And if you look at a quantum computer, these are some of the requirements of modern technologies. So the system should be scalable. To should be able to initialize the state of the qubits to a simple state, as the one I discussed a little bit earlier, and a universal set of quantum gates and a qubit-specific measurement capability, and long coherence times. And these are typical platforms which many people are working on. So at the University of Oslo, we have activities on spin qubits in quantum dots, but also so-called point defects in semiconductors. It's an active research field. So experimentally, we do have some activity in this country, although we are really lagging behind compared with Denmark, compared with Sweden and Finland. Finland has actually moved, they're the world leading producers of dilution fridges. There's a small digression here. Since there's a scarcity of helium-3, which is used in the dilution fridges, Bluefors, this Finnish company, has teamed up with a US company, which is going to harvest helium-3 on the moon. This is not science fiction. This is happening. So anything, any of these platforms which can be implemented at room temperature, if somebody can develop that, there is a party in Sweden which you probably will be invited to. You meet the Swedish king and you get a diploma and so on. So most of these platforms here, as you see, they actually cool down to basically 0 Kelvin. So I've been collaborating with people in the US on using electrons on liquid helium. And obviously you see then that you have to have liquid helium to do that. And these are systems which are cooled down to nanokelvins. And they are very susceptible to thermal excitations. And they often deep down in a basement. They have to be made shockproof to small vibrations in the soil, to earthquakes, etc. So it's a very expensive setup. So this is something which, we just went through that. I wanted to come back to the statement which I put up before the break about the relevant degrees of freedom. So some of you have taken a course in machine learning, and you may have heard about something called barren plateaus, right? These are typically plateaus where your gradients in the optimization part flatten out and go to 0. So when you set up the relevant part of the Hilbert space, which is amenable to classical simulation, then this is then related back to that statement about the efficient degrees of freedom of a system. So the word is relevant because there are several scientific articles that start to give a more precise meaning. So the barren plateaus which you encounter in the algorithm which we are going to look at, which is called variational quantum eigensolver, that has often been traced back to the fact that most of the states in this huge dimensional space are essentially chaotic and irrelevant. So when you're setting up, when I set up a big diagonalization problem, so for those of you who have taken a course in many-body physics and have studied full configuration interaction theory, I can diagonalize, let's say, 1 billion times 1 billion Hamiltonian matrix. So when I look at the states then, a linear combination of the states, I will see that most of the states are irrelevant. Perhaps there are 10 to 100 which have a coefficient which is non-negligible. So that tells me out of this billion of degrees of freedom, there are perhaps only 10 to 100 which matter. So this goes also back to when you do a machine learning implementation of a neural network to solve Schrödinger's equation. You can have millions and millions of parameters representing weights and biases in a neural network. And you're not able to extract a physical meaning from that. And many of these parameters are irrelevant for physical understanding. So what we often want to is to understand what do the laws of motion do to the system, and can we extract from a complicated calculation a simple message where we can simply state that this is irrelevant physics. Okay? So there's actually a lot of research on what you might call explainable AI, but also explainable quantum computing. And because at the end, we are going to have many parameters, we are going to have a multi-dimensional space where we want to find the minimum. So there's an optimization problem. And in this optimization problem, there's a problem which persists in all kinds of AI implementations, which is called barren plateaus. And that's simply that many of the states in this huge monstrous space can be just negligible. To understand that, that is actually one of the central questions. Okay, so this was actually, if you remember back that statement which I put back in black here. So I had it, I've exposed you to all this kind of blah blah in the slides here, but I put this statement in black here because at the end, whatever we do, we want to extract a simple message. which you can tell your friends in a Friday evening at a party. This is a simple physics. And you probably heard me saying this joke. I have a suspicion of why people don't invite me to parties anymore. But this is a kind of topic which I think is central to whatever we do, actually. Okay, so what I want to do now is actually to come to the relevant mathematics which we need. So I would also recommend you to take a look at some of the things, because I won't have time to go through everything, but I will pick up some of these topics next week as well. So, but today I will just stay with the whiteboard. No, with the slides, sorry. So in the beginning here, there are just some simple notations, which is just for the set of completeness. And if you're a little bit rusty on the standard notation in quantum mechanics, I just wanted to remind you of the way we represent vectors, standard linear algebra. This is the way you would typically see a vector with n components, its transpose, and then we have the Hermitian conjugate. So I will often use a little bit more sloppy language, because sometimes to say Hermitian conjugate, it just becomes pretty long. I will just say the conjugate. So but you should be able to see from the context what we're actually doing, okay? But these are just basically what these expressions mean. And we also know that we have the inner product. And in case we have a complex vector, this is given like that. So I hope you don't get offended if I remind you of some of these basic things. Yeah, you can see here. So sometimes, as I said here, I will just call it so the Hermitian conjugate, as you know, is by taking the complex conjugate and then taking the transpose. Sometimes I just say the transpose, sometimes I just say the conjugate, but you should be able to understand that from the context, okay? And unitarity plays a central role. So we are going to look at systems which will behave as unitary system, and that's an essential element in quantum computing. So you have to have unitary operations. That's a basic. Another thing which I wanted to remind you of is the outer products and inner products. So we have the outer products of two vectors gives a matrix. That's essential because we will define pretty soon a quantity called the density matrix. So how many of you have encountered the density matrix? Okay, some of you have. And the density matrix is just given by an outer product. So this is a quantity which we will compute again and again in this course. And the density matrix is something we use to calculate expectation values. We also use it to assess something which is called a von Neumann entropy, which we then use as a measure of entanglement. So entanglement, you will see how to measure that is something which is tricky experimentally, because it's not an observable. It's a theoretical quantity, and that means that when we relate that to experiment, an experimentalist has actually to reconstruct the density matrix. And the density matrix leads to also different ways to analyze the entanglement of a many-body system. So these are key topics which we will discuss next week. And then this is just to remind you of the matrix. I will often rewrite the matrix in terms of the column vectors. And boldface quantities, lower key letters are vectors and upper key letters are matrices. Just notation here. And then we have tensors as well. So I'm going to skip some of these things here because I wanted to simply go back to the quantum mechanical definition. So this definition which you saw now, we are going to replace it with that one, okay? So that's the kind of notation I will use throughout the semester. So probably some of you have seen this notation quite frequently. Some of you are a little bit more rusty, but this is the basic notation. This is the Dirac-Braquet notation. But it essentially, mathematically, this is what it means. And then we have the Hermitian conjugate. which we will write like this. And that means that the inner products is going to be written in the physics way, not the way the mathematicians like it. So we're going to write it like that. And that's also the inner product between two arbitrary vectors. They obviously have to have the same dimension. Keep again that this is always a real number when you have the same vectors. And while for different vectors is in general not equal to xy, which you can see from an example on the next slide here. So these are also just some things which you probably are familiar with. Okay. And if you take this vector here, you will then see that this gives you, when you do the mathematics, just gives you a number, a real number, as it should. But if I take this one, then you see that if I take this vector here and that one, these two vectors, then what you will see then is that these different inner products actually give you different results. And that leads to this important result, which you probably have seen many, many times. Okay, just examples. So this is meant as a quick reminder. And then in addition, you have the outer products, which also play a central role. Now, you will see again and again that these Pauli matrices are going to play a central role as 1-qubit gates. And they have their commutation relations, and we also know that when they're squared, they give us the identity matrix. So the Pauli matrices are unitary matrices, meaning that the inverses are equal to the Hermitian conjugated matrices. And the determinants are always equal to 1, which you also can verify easily. And they have the famous commutation relations. So I'm going to now bring up again the computational basis. So we will start with a 1-qubit basis. And this has 2 states. And you can see now that these states are orthogonal. So keep in mind again that this could be a classical representation. So there's nothing quantum mechanical here. However, these states could also be the eigenstates of a quantum mechanical operator. But I will normally call these the computational basis states. I will often call them just the classical basis, because this is something you can define classically and write down. Okay. And there's no need for quantum mechanics to set up these states, right? So this could just represent true, false, right? It's a binary system. Just one other way to represent a binary system. But for us, this will serve as the computational basis, which means that we have now 2 states, bit 0 and bit 1. And it's easy to show that these are form an orthogonal basis and a normalized basis. So the acronym which I will use quite often is just the ONB, orthogonalized and normalized basis. And we know that if I take the identity operator, this is the completeness relation for these 2 states. This, if I now take the outer products of 1, 0 and 0, 1, if you just do that, and this is something for next time, just take a look at all these kind of repetition elements and just convince yourself, because this is just some of the basics which we are going to use again and again. Now, the thing which is also important is actually the one of projection operators, because we can write this I as P plus Q. So, and when we act on a state, then these operators will actually project out one of the components, either 0 or 1. So these operators, which you see here, represented by matrices, are idempotent. Their determinants are obviously 0. This is a definition of, part of the definition of idempotent operators. So we cannot use these operators for unitary transformations. Just keep that in mind, right? So the reason why I bring this up is that these operators, which you see here, like this P or Q, they are used in the measurement stage. because they will then project out a specific component. So let's just see that on the whiteboard here. So let's take a quick look at it so I can convince you about what I'm saying here. But if you think of the basis states which we have, so we have a basis state which I label like a 0, which is given now by 1, 0, and 1, which is given by 0 and 1. Then if I take this matrix P, which I've defined, this is given by 0, the outer product of 0, which is simply given by 1, 0, 0, 0. And then similarly, this operator Q is then the outer product of this specific state, and that gives us 0, 0, 0, 1. And then the identity in this case is just given by P plus Q, which here, since we have the only two states, I equal 1 up to 2 here, actually I should set 0 and up to 1, since I'm labeling this from 0 to 1, like that. Okay, now then comes superposition. So if we look at the quantum mechanical principle of superposition, what we have is that we can, with this basis now, we can construct a general state, which I will call for psi, which is now given by some alpha multiplied with a qubit 0 state, plus a beta multiplied with a qubit 1 state. And now you can see when I make a measurement, and suppose now my measurement operator looks like this P operator. So if I act with P on psi here, you will then see that this is the same as having 1, 0, 0, acting on alpha multiplied with 1, 0, plus beta multiplied with 0 and 1. And when you do the algebra here, you will then see that this projection collapses to the state 0. If I act with Q, it collapses to the state 1, with these coefficients either alpha or beta in front of it. So this one becomes equal to alpha times 0. So we have projected out a specific component. So this is something which we will use when we now define later, which is next week, measurements. So in the slides for this week, you will also find the definition of measurements, but these slides this week contain a little bit more information than what we will cover. And that's why I would like to ask you to take a look at these elements. And some of these elements we will pick up next week and go through in more detail. But we won't have the time to repeat all of linear algebra by obvious reasons. Okay, so let's go back to the slides. Any questions so far? So these operators, and you see again, this is the kind of same stuff which we had here. So this kind of coefficient alpha is just the overlap between the state psi and 0, and the same with beta. And that represents the overlap between the computational basis states and the state psi. So this state here could be a physical realization of our system. And we don't know whether the system is in state 0 or state 1. And then you see that when you compute the inner products, you get 1. And since the new basis, which is defined in terms of a unitary orthogonal transformation, preserves the orthogonality and norm of the original computational basis. To see this, you just compute I have an example on how you can show that unitarity is preserved. And you can see now, this is just what we did on the whiteboard here. So essentially what you see here is just a kind of summary of what we did on the whiteboard. The density matrix, a central aspect, and this is roughly where we will stop today. The density matrix is now defined as the outer product of this specific state. The density matrix is going to play a central role in many, many aspects in quantum computing, and also in modern quantum mechanics. This serves as a way to define in a very elegant way many properties like expectation values of specific operators. So we know that the trace of the density matrix is equal to 1. That's a very important aspect. And I also wanted to bring up, before we take a break now and meet again next week, there are specific operators which transform into gates, and one of these is the Hadamard gate, as we will see later. So we are going to represent that as a specific gate. And what this does, if you have prepared the 1 qubit state, so this is a 1 qubit gate, it's a 2 by 2 matrix, and it acts on this 1 qubit basis, which we have defined. And you see now that when I act with H on 0, I make a superposition. If I act on H with 1, I perform a new superposition, which is a new state. And these two states are actually orthogonal to each other. You can see that. And another famous gate operation is the so-called phase matrix. And these are all gates or operations which can be related to physical processes. And then the final thing which I just wanted to say is that if we have now a space, a complex space for 1 qubit, which is 2-dimensional, and then I couple that one, the tensor product, then we will use the more compact notation like this. So instead of carrying with us this kind of notation here, we are simply going to write in a compact way. And this is the tensor product of 2 states. So often when you look at text in quantum mechanics, the notation can be deceiving because this actually means that. So if you take the spatial degrees of freedom of a state and the spin degrees of freedom, that's actually a tensor product of the spin degrees of freedom and the spatial degrees of freedom. And you would often write it in a compact way because to write it like this becomes cumbersome. So this is what it means. And the states which I wanted to end the lecture today with, where we will pick up again next week, we will now get a new computational basis. And this basis is a 4-dimensional basis. It has 4 states. So I can do 0, 0, which I would write like this. I can do 0, 1, which becomes this vector. And similarly, I can now do the remaining ones, which give me 1, 0, and 1, 1. So I have a 4-dimensional space, and this is an orthogonal basis. And it is something which we will use as a computational basis for 2 qubits. So this could be 2 electrons in 2 different harmonic oscillator wells. So 2 different physical systems, which we then couple together. So often you will see a subscript like system A, system B, but then for simplification, you just write it like what you have here. And then you can make linear combinations of this, which can be written as products of states or entangled states. You can proceed then, you see now you can set up 3 qubits, etc., etc. So this notation becomes a little bit cumbersome after some time, and we will introduce some simplifications next week. So at the end here, so you will see there are more things here which we will discuss a little bit more in detail next week. But there are some basic exercises which you could take a look at just to remind yourself of important topics which we will use, like commutator identities, properties of Pauli matrices, just to convince yourself. Shared eigenvectors, and then write a small function which implements, let's say, the Pauli matrices acting on a 1 qubit state, because we will need that in the setup of the projects. And then you can do the same thing with the Hadamard and the phase gates. Because this will be basic operations we will repeat again and again on the qubits when we set up what we are going to call a parameterized quantum socket. Okay, I'm going to stop here now.